So let's first talk about sampling a continuous time signal. So the first thing we're going to concentrate on is what's called ideal sampling. So ideally, what we're doing, the mathematical model of what we're doing is we are taking our original signal and we represent our sampling signal as a train of impulses where the impulses are separated by the sampling period. And when you multiply those signals together, you get this set of impulses that takes on the shape of our original signal. So original signal we'll call X sub A. A is just for analog. Our sampling signal is a sum of impulses that are just shifted in time, and they're shifted in time by the sampling period. Those two signals are multiplied together to get the sampled signal. Now it's important to note that this is not the digitized signal. This is still a signal in the time domain, which then goes to a digitization process. But nevertheless, this represents the sampled signal. And what it is going to do is just pick up the amplitudes of the original signal at those sample times. So that is our mathematical way of expressing the impulse sampled version of x of t, or the ideally sampled version of x of t. Like I said, x sub s is still a continuous time signal. Question is, how dense or how small do we have to make our sampling period to make our sampled version accurate enough? In other words, what are the restrictions on the sampling period, or equivalently the sampling frequency? And to answer these questions, you actually need to analyze things in the frequency domain. Okay, so let's take a look at those two signals that constitute the sampled signal. So first off, we know that we came from a pulse train and we ended up with a sampled version. Well, that pulse train, that impulse train I should say, is a periodic signal, which means it has a Fourier series. And if you go to the definition of a Fourier series and try to find out what those coefficients are, they just turn out to be a constant, 1 over Ts for all k, for all coefficients. And that means that we can express our impulse train, as a Fourier series rather than as a bunch of impulses. Okay, so now let's consider our sampled signal, which we got from multiplying x of a and p of t. Now we just take x of a and carry it inside this summation. So this, carrying out that multiplication, we get this. But that is not periodic. Therefore, it does not have a Fourier series, but it should have a Fourier transform. So our sampled signal, x of s, should have a Fourier transform. Well, if we take the Fourier transform of both sides, then we can carry that summation outside of the Fourier transform because it's linear. So then we just look at the Fourier transform of what's inside the curly braces here. Well, that is from the modulation property. That is just the Fourier transform of the original signal, x of a, but we get multiple copies of it at these frequencies, k omega s. Okay, so really this is just modulating xa of t with a phasor at a frequency of k omega s. Remember, omega s is the sampling frequency. So let's think about what this looks like in the frequency domain. So first off, the time domain of our original signal looks like this. Let's assume that the frequency domain of that signal looks like this. So now the time domain of our sampled signal looks like this. What does the frequency domain look like? Well, we just get shifted copies of the original spectrum. That's what this expression is saying. Okay, so what does that mean for reconstruction? So we're sort of jumping ahead of ourselves, but think about it. If I want to recover this signal, xa of t, then equivalently, I want to recover this spectrum. We'll take a look at this signal, the sampled signal, or the spectrum of the sampled signal. I should be able to do that if I can filter out all the rest of this crap. And note that that original spectrum, we just get these multiple copies of that spectrum. So let's assume that we have a high sample rate. So we're actually sampling at a pretty high frequency, which means the sampling period is actually quite small. So our time and frequency domain for our original signal look like this. If we sample, then the time and frequency domain of our sampled signal look like this. And let's say we put a low-pass filter around, at the end of this sampled signal, then that means I get this spectrum, which means I can perfectly reconstruct my original signal. So we're starting to get an idea of what's necessary in order to allow perfect reconstruction. So what happens if we don't sample at a high enough rate? So let's assume that our sampling frequency was actually kind of low, which means the sample period is actually quite large, or the spacing between samples. If we don't sample high enough, then those spectra are actually going to overlap and add to each other. And then if I do a low-pass filter on that, I get this, but that is not at all close to the original spectrum, and I don't know what I'm going to get in the time domain. I certainly am not going to get this original signal. And so this starts to give us an idea of what's necessary to allow perfect reconstruction. And what we say is that as long as a signal is band limited, that is to say, as long as its Fourier transform is limited to a certain frequency range, as long as it's limited to a certain frequency range, then we can actually reconstruct it. So let's think about if we sample high enough, the spectral copies are separated far enough apart. If we start to reduce the sampling rate, then at some point those spectral copies actually touch each other, and then below that they're actually interfering with each other. Now what if we had a signal which is not band limited? That is, that its frequencies were not restricted restricted to be non-zero in a certain range. Let's say it was non-zero everywhere. Then it doesn't really matter what my sampling rate is. So this is actually a high sampling rate, medium, low, but they're still interfering with each other, and there's no way to filter it and recover this spectrum. So let's go back to our band limited signal again. So defining what band limited means, it means that it's non-zero only in a certain frequency range, and it's zero outside of that frequency range. And again, just taking a look at what happens as I decrease the sampling rate. So if my sampling rate is quite high, I get no overlap. As my sampling rate goes down, the sampling frequency, then Fs is sliding closer and closer to Fmax. At some point they start to overlap, and then at past that point we actually have a fair bit of overlap. As long as that original signal is band limited, it can be reconstructed from the sampled version, but only if those spectral copies do not overlap. And that basically says that Fs, this is going to be the trailing edge of that spectrum, and that's at Fs minus Fmax, and that has to be greater than Fmax in order to avoid overlap. In other words, our sampling rate has to be at least twice as high as the maximum frequency of the original signal. And that's what's called the Nyquist sampling criterion. Not sampling criterion, sorry about the spelling here. So for an impulse sampled signal, so this is all depending on the idea that we have done ideal sampling. So an impulse sampled signal, for it to form an accurate representation of the original signal, the sampling rate has to be at least twice the highest frequency in the spectrum of the original signal. Now, when you do not sample high enough, then we get this case down here, you get an overlap of the spectrum, and that is what is called aliasing. So when you hear that term, what that means is it's almost always, in the signal processing industry anyway, it is associated with not sampling at a high enough frequency. And you end up with, I don't want to use the term ghosting, but that's sort of the idea of what's going on. You end up with strange repercussions on any reconstructed signal, let's say. And we're going to take a look at those in the labs. Okay, so in practice, we don't want to go with the equality because I'm just going to go back for 1 second. We don't actually want to be in this case where they're just past overlapping, because practically speaking, that's actually pretty difficult to do. We want to allow for a sufficient margin between those spectral copies because there's always going to be imperfections in the system. There's going to be imperfections in sampling, and there's going to be imperfections in reconstruction. So we actually want to choose our our sampling frequency a fair bit higher than the 2 times F max. Now, those sampling frequencies are typically fixed by the constraints of the hardware. So if you go to higher sampling, that means more money. And we often don't know the frequency range of the signal that's coming into the system. So we don't know what that maximum frequency might be. So for example, if we were sampling speech, the highest frequency component of someone's speech actually depends on who the speaker is. So somebody with a high-pitched voice actually has higher frequency content. Somebody with a really bass or low voice has, or low-pitched voice actually has lower frequency content. Therefore, it's easier to sample. So usually we just say, well, what's the extreme? That's going to be what we design our system for. And probably the biggest implication of this practically is that we've quote-unquote forced the signal to be band limited. What we do is we say, okay, well, I'm going to design my system for this maximum frequency, and the way I'm going to do it is no matter what the signal is coming in, I'm going to filter it. And what it's called is an anti-aliasing filter, and that is a fundamental component in any sampling system. So we have a transfer function. This is an ideal filter. A transfer function, a low-pass filter for any signal coming in, and basically we've picked a sampling frequency for an extreme and we design a filter for that extreme. And then we do the sampling. And that means that we've already made the incoming signal into this sampler. We've made the income signal band limited just by sticking in this filter.